In Module 2, we study various digital modulation techniques. The important topics in this Module 2 are phase shift keying, generation, detection, and error probabilities of binary phase shift keying, quadrature phase shift keying using coherent detection, its generation, detection, and error probabilities, and M-array phase shift keying and M-array quadrature amplitude modulation. So there are 8 questions that you are going to get from module 2 part 1, 3 questions from topic 1, 3 questions from topic 2, and 2 questions from topic 3. So let us try to understand the principle of phase shift keying technique using coherent detection. Binary phase shift keying is a system in which a pair of signal, that is S1 of t and S2 of t, which is used to represent binary symbol 1 and 0, are represented by equation as shown S1 of t and S2 of t. Since these are baseband signal binary symbols, so I need a high frequency carrier in order to represent the analog waveforms here. So to transmit binary 1, we are transmitting in phase signal, that is carrier. So with respect to this equation, Fc represent carrier frequency and TB represent bit duration and EB represent energy per bit duration. Similarly, S2 of t, that is to transmit 0, we are going to transmit out of phase carrier. Here we are able to see 180 degree. Therefore, binary 1 and binary 0 is represented in BPSK by sending in phase and out of phase carrier. So what is signal space diagram of BPSK? Observing the general equation, that is as shown here, that is S1 of t, S2 of t. Here carrier expression is common in both signal. Therefore, we are going to consider the orthonormal basis function, which is known to the transmitter and the receiver as square root of 2 by Tb cos 2 pi Fct for Tb duration. So with this substitution, S1 of t, that is this expression, can be written in terms of orthonormal basis function, that is square root of EB phi 1 of t and S2 of t minus square root of EB phi 1 of t. From the fundamentals, finite duration energy signal can be expressed in terms of orthonormal basis function and vector values. So how to find a vector value here? So to find S11 for the first signal, we have to multiply S1 of t with the orthonormal basis function and integrate over Tb duration. Because of orthonormal properties, phi 1 square of t when it is integrate over Tb duration yields unit magnitude. Therefore, S11 first vector value will be Eb, root of Eb. In a similar way, S21 yields minus square root of Eb. So there are two regions here, Z1 and Z2. So in order to decide which symbol was transmitted, let us consider a decision boundary here. And let us consider this orthonormal basis function on x-axis. So phi 1 is shown here. So here locate this point plus square root of EB, which is representing message point 1. So here is that point, and minus root of EB located on left hand side, that is second quadrant. So for BPSK, this will be the signal space diagram, because we are transmitting only two signals, S1 of t and S2 of t, to represent binary 1 and binary 0. The next important concept here is the block diagram of generation of BPSK signal. We want to transmit binary data sequence. So in order to transmit binary data sequence over analog channel, from the fundamental equation of BPSK, which is shown here, orthonormal basis function is common, that is carrier function is common, its nature is known to us. So the next very important thing here is to generate the amplitude, that is plus square root of EB and minus square root of EB. So to generate these two levels, we are going to use a encoder immediately after binary data sequence. So when binary data sequence is applied to polar non-return to zero level encoder, that is polar N or Z encoder, it produces square root of EB or minus square root of EB, depending on whether the bit is applied as 1 or 0 respectively. So now at the output of encoder, depending on the binary data sequence, you are going to observe here at this point where I am highlighting, you are going to get square root of EB or minus square root of EB. Now this is multiplied with the orthonormal basis function, which is nothing but the carrier, with amplitude square root of 2 by TB with carrier frequency FC. When these two are multiplied, we are going to get binary PSK signal depending on the bit that you want to transmit here. If you want to transmit 1 square root of EB, this is produced at this point and it is multiplied with phi 1 of t to get S1 of t. If 0 is applied, minus EB, you are going to get minus EB into phi 1 of t is nothing but S2 of t here. That is how generation of BPSK signals is obtained. So the next very important concept here is detection of binary PSK signal. If this is the transmitted signal S of t, when it is transmitted over analog channel, additive white Gaussian noise is added to the transmitted signal. Therefore, corrupted signal is received at the input of the receiver. When that signal is passed through the correlator, which produces a real number, that is x1. Here what is phi 1 of t? Phi 1 of t is nothing but the carrier that is used at the transmitter, which is known to the receiver. That is why we call it as coherent detection. Now here the output of correlator is a real number. This value is compared with the decision device threshold. If x1 is greater than 0, this decision device will choose 1. That means for TB duration, binary 1 will be generated. If x1 is less than 0, this decision device chooses 0. For TB duration, 0, binary 0 will be generated. That is how, depending on the value of x of t, that is x1 here, we are going to recover the transmitted signal at the transmitter here. So the next important topic here is, what is the error probability of binary PSK using coherent detection? There are two kinds of errors that we are going to see in binary PSK. If this is S1 of t, if S1 of t is transmitted, it may be decoded as 0. If S2 of t is transmitted, it may be decoded as 1 because of noise. Therefore, two kinds of error will be there. Error of first kind will be S2 of t is transmitted. This is S2 of t signal space diagram. Because of noise, this signal falls in region 1, that is Z1, and the receiver decides this S2 of t in favor of S1 of t. So the second type of error is S1 of t is transmitted. Because of noise, the received signal falls in region Z2 and receiver decides in favor of S2 of t. So to calculate the probability of making an error of first kind, so let us consider the region Z1 here, whatever we have shown here. So here x1 is greater than 0, less than infinity. So whatever the value that is produced by the correlator is greater than 0 but less than infinity here. Now the observation element, this x1, is related to the signal that is received is given by this. X1 is equal to integral 0 to tb x of t, that is nothing but received signal. And what is phi1 of t? Basis function or the carrier transmitted at the transmitter here, which is known to the receiver. So now the conditional probability density function of a random variable x1 given the symbol 0 which was transmitted is defined by this expression. What is S21 represent? It is second signal transmitted, that is S2 of t transmitted. What is x1 here? That is nothing but observable element. So you substitute S21 is equal to minus square root of EB and you simplify this. When we simplify by using substitution method, we are going to get the probability of error. That means 0 transmitted and it is identified as 1, that is given by a Q function square root of 2EB by N naught. Since the conditional probability of the receiver in deciding favor of symbol 0 given symbol 1 has also same value, therefore probability of error for binary PSK using coherent detection is as shown.